one thing is something I'm going to change starting now, and one thing is just a recommendation for you. So 2 things about daily assignments. The daily homework. The first one is part of the assignment, and I'm sorry if I am misreading this, but part of the assignment is you don't remember everything from the, you can't remember everything from class from just hearing it live. Just like in other classes, there's a reading assignment, In this class, the start of the assignment is reading back through the notes. So some people maybe have been doing that. I think not everybody has. I think you sort of feel like you want to get right to the problems, but you're going to be better off if you take the time. I don't think it'll take that much time to just read through the notes, work through the example problems, understand how to do those, because those are meant to guide you on these homework problems, and then go to the homework problems, okay? So before you start the problems, read the notes. Did I start this? Yes. And understand the example problems. If you haven't been doing that, you'll be surprised how much that helps you make sense out of the homework problems. And the second thing, this is something I'm changing starting now. These assignments, I'm going to cut down a little bit on the number of problems that I ask you to do without the solutions. But then these daily assignments are also going to include going back over problems after I've posted the solutions. And then the quizzes, so it's now going to include problems that you have to try to solve like before. Again, like on most of these, there'll be example problems that you can follow in seeing how to do these. And the new thing that we're going to do is problems, old problems that you have the solutions for. And so the quizzes will be on all of those, and I'm trying not to increase the amount of time or anything that you have to spend on these. But the idea is just that you spend some time trying to do new problems, and you spend some time making sure that that you understand the problems that the solutions are posted for, and that means also that half of the quiz points or whatever are going to be based on things that you already have the solutions for. So I think it should increase the quiz scores a little bit, and it also should, hopefully, my hope is that it builds good habits, because after you've tried these problems, you're making sure that you've done them the right way. That's all. Anybody have any questions about these? So this one, the second one, that'll be clear once, it'll be posted in the assignments. But this one, just the notes for this class are the only textbook. I'm trying to make it very clear what stuff you need to understand. But I expect you to understand, to remember that stuff, understand it well. And so before you start working on the problems, you need to read that stuff. Okay? Anybody have any questions about homework or anything like that right now? All right, so let's start with a problem for you to work on. So a basketball player shoots a ball at 50 degrees above horizontal. From 1.5 meters high. If the basket is 4.572 meters away horizontally, that's 15 feet, that's a free throw. And 3.048 meters high, that's 10 feet, that's the height of the basket. First, what's the speed that the ball needs to be shot at to make the basket? And second, how high is the ball at the highest point? Okay, so let's break up into groups about like last time and try to work through those problems. And I have markers, so when you're done, find a space on the boards and write the solution up, okay?
There we go.
Okay, everybody shut up for a second. Bullet shot horizontally. At the same instant, another bullet is dropped. From the same height. And okay, it's shot horizontally with a speed of let's call it V0, capital V0. So part A, how long until the shot bullet hits the ground? B, how long until the dropped bullet hits the ground? And then C, what conclusions come out of this? So what do you expect to happen? What do you expect the answer to be? They're gonna land at the same time. So see if you can work through those two and see that that happens. The next topic I want to go into is relative motion. So we did this in one dimension, and it works exactly the same way in 2 and 3 dimensions. And so relative motion says the position vector of A relative to coordinate system B is equal to the position of A relative to coordinate system C plus the position of C relative to coordinate system B. So you can think of it like this. If you have, so say this is coordinate system B, this is coordinate system A. Whoops. Let's make this coordinate system C, and then let's call the object that you're tracking A. Okay? Then what would this vector be called with that subscript notation? That's right. This is the position of A relative to B. And what would this vector be called? That's position of A relative to C. And then what would this one be called? Yep, position of C relative to B. And you can see that with the rules of vector addition, PAB is equal to PCB plus PAC because you put the tail of one at the head of the other one, and the resultant vector goes from the free tail to the free head. So it's just following the rules of vector addition. One thing to notice about this is these two coordinate systems, and we're talking about B and C in this example. The origins are in different locations, but they must have the same axis orientations. If they don't have different origin locations, there's not much point in doing this. They're the same coordinate system. Well, you can take the time derivatives of all these and get the other two relative motion equations. The velocity vector of A relative to B is equal to the velocity vector of A relative to C plus the velocity vector of C relative to B. And then the acceleration version, acceleration of A relative to B is equal to the acceleration of A relative to C plus the acceleration of C relative to B. And what's different in this case than in one-dimensional motion is that all these things aren't happening parallel to each other. Now they're vectors. So you can have one of those coordinate systems moving this way and the object moving this way, you know, and still be able to track that. In one-dimensional motion along a line, we couldn't do that. So let's see a couple examples. So let's say that you have a cart with a little launcher apparatus on it, and this launcher shoots a ball straight up into the air at 4 meters per second. Okay? Now have the cart move 3 meters per second to the right. And let me give a distance between where the, let me give a height between where the ball's launched from and the ground. So how far away horizontally will the ball hit the ground compared to the launch point? Okay, so who can give me a strategy for this problem? What are we going to do as the steps? Or how can we use this information? It's a free fall problem, so it's going to end as a free fall calculation. But how's relative motion going to get in there? Yep.
Well, the ball would be moving at 0 meters per second relative to its start.
Right.
Relative to the
Yep.
ground. So then it'd be moving a few meters.
That's right.
To the ground.
That's right. So the initial velocity of the ball. So to calculate the velocity vector at the launch, we're going to say the velocity of the ball relative to the ground is equal to the velocity of the ball relative to the cart plus the velocity of the cart relative to the ground. The velocity of the ball relative to the cart, what's that going to be? That's the ball relative to the cart is going to be 4 meters per second up. Does that make sense to everyone? So 0, 4. The velocity of the cart relative to the ground, yep, is 3, 0. That's in the x direction. So the velocity of the ball relative to the ground is 0, 4 plus 3, 0. So that's 3, 4 meters per second. And now we can go through this calculation. If we say our time equals 0 at the instant it's launched, time final is when it hits the ground. The origin location, let's say it's on the ground right beneath the launch point. The axis orientation is going to be y up, x in the direction of the cart's motion. So which coordinate system orientation are we talking about? The orientation of the ground coordinate system or the orientation of the cart coordinate system? Yes. Anything else? Yeah, both. Because, right. Because somewhere I said that. Notice, they have to have the same orientations. Okay. And now for the variables, time final. We don't know. Acceleration, x is 0. AY is negative 9.81. P0x is 0. P0y is positive 0.2. V0x, that's what we just calculated, was V0. So the x component is 3. The y component is 4. P final x, we don't know. P final y is 0. Yes. V final x, we don't know, and V final y, we don't know. Okay, so the strategy for this, it's a pretty common strategy. This comes up a lot. We're going to use PFY is equal to P0y plus V0y PF plus 1/2 AY PF squared to find TF, and then we'll plug that into the x equation. So we have 0 is equal to 0.2 plus 4 TF minus 4.905 TF squared. So you can use the quadratic formula on that. There's A, B, and C. Can someone solve that? I don't have that here. Okay, PF is what? 0.8628, and there was a negative one also. Is that right? Yeah. Okay. So yeah, this is the one we want. We want the positive one. And now we can plug that into this equation. PFX is equal to 0 plus V0x times TF plus, there's no x acceleration, so what do you get for that? Uh, 2.588 meters. Okay, here's one more for you to work on. I don't know. This is the last thing we'll do today. Maybe you'll probably have time to get through this, I guess. It can go pretty fast. So here's the river. And it's 0.1 meters across. And here's the swimmer from above. Those are his feet. No, that's the how far it is. That's not the speed.
I mean, it's only 0.1 meters across.
Pretty small. That's big. A tenth of a. Oh yeah, you're right. That's tiny. I was thinking of a mile. That's not much of a river. Okay. No, that's true. Okay, thank you. Let's call it 50 meters. Okay, that makes a lot more sense. And let's say the river is moving, this way at 5 meters per second. And the swimmer can swim 4 meters per second. If the swimmer aims directly across, how far is he downriver when he reaches the shore? That's, you can be sure, you can calculate it.
Well, you never know that he's going to make it for sure.
Oh,
Calculate what he
yeah, right, he could,
does.
yeah, like a crawdad could bite his foot or something. You never know.
All sorts of things can happen.
A shark could eat him.
In a river.
River?
How far is he down? I'm glad we didn't use that tenth of a meter.